So sorry for the delay. We are eventually done with the settings. So I would like to first start by thanking the Optical chapter from the University, Etienne State University, and so that board is representing. I would like to thank in general my friend Rafika Kostan. I will have the opportunity to say a word at the first slide. And I would like to share with you that beyond this talk, actually, that will deal with photonic bandgap physics in general, but in a particular context of helical anisotropic medium, which means chirally structured optically anisotropic materials. And usually those kind of materials are very well known to manifest nice colors through their photonic bandgap properties. And here I would like to show through two main lines of research some examples that we can do much more than nice colors using helically structured anisotropic materials. And as a starter, I would like to say a few words about my link, my personal link and scientific link to Armenia, which actually are long-standing. Since it is already 20 years ago, I did my PhD with Etienne Brasselet, who is working in Canada. That most probably many of you are knowing personally. And it is at that time that I met Rafik when he was visiting a professor in Laval University in Canada, in Quebec City. And since then, I made several postdocs at different places, and then installed myself in Bordeaux University in France, where since several years, actually had a chance to work with Armenian students and PhDs that are there. Arthur, David, Musher, that is around, and Lagashak, actually, that is just starting his PhD. And so it's really a long-standing scientific collaboration with Etienne State University in a very particular way, actually, because all these guys were so far coming to Bordeaux after discussion with Rafik and recommendations by Rafik. And actually, it was and it is still a real pleasure to host Armenian young scientists and to do a bit of science together, and maybe even more this time, as I will already try to do with Musher, as you know, he's studying himself here. So let me start. This talk, yes, Rafik.
I'm sorry, you forgot that you help also Amalia Minassian.
Yes, Amalia was so not directly in my group. Actually, that's why I was not mentioning. But it's a good point to recall. Amalia actually published a paper together in collaboration with a group in our lab, a terrace group. And now Amalia is working in a high-tech photonic company to develop infrared and terahertz camera in particular. And I have to add for the younger generation that all these guys got jobs in research and development, good companies. So Arthur and David are in France, and Musher is back to academic in Armenia, and Vagashak is the next guy, so we'll be able to tell you in 2-3 years. So, and so I was speaking about the topic, which is embedding helical structured materials, which means there is an even more general concept behind this, which is chirality. So chirality is really the main actor of my talk, so I have to introduce the main actors. And chirality is simply the fact that you will be said to be chiral if you are not superimposable with your mirror image. That is a basic definition regarding symmetry breaking. And this applies to any spatial entity at various scales, from astronomical scales to bio nanoscales with DNA helices, for instance. And what is important is that chirality is really across length scales in the sense that when you have a given body, like us, we have right hand and left hands, but inner constituents of us could be of other chiralities as well. So actually you have a hierarchy of chirality in a given material system. So you have different levels of reading chirality and of using chirality. And this is what we will do here. And very importantly, as I introduced chirality as a symmetry breaking definition, it means it has nothing to do with matter. I was showing matter to exemplify it, but this applies also to field, abstract quantities. So in particular, light. So light can be color. So and to have a simple framework, because this is what I will try to do along this talk, is to convey main messages with very few basic informations on which, with the help of a few qualitative statements, we will be able just to catch up what's going on in our scientific developments without resorting to technical details. So let's take the very simplest way to describe a light field, paraxial light, which means you just neglect the transverse coupling. And it happens that, in that case, any field, here, electric field, will be the same for the magnetic field. It's described by the simplest expression for a monochromatic paraxial field. You have an amplitude factor that depends on space, that is beam shape. You have a propagating usual factor, and you have a vector that describes how the electric field is varying in time. So that's the polarization state vector. It's a complex vector. And there are a family of them, and there are two specific situations where this vector has this expression, x plus minus I y. And in that case, we are dealing with this, what you are most probably all familiar with that, with circular polarization states of light. In that case, this defines in space for the electric field configuration. If you make a snapshot of the electric field at a given time, the electric field configuration is an ellipse. This ellipse will be either left-handed or right-handed. So here you can enjoy really the helical structure of circular polarized light. And all this can be described in a general way using the formalisms of the polarization ellipse. So circular polarization states are simply a particular case of polarization. And during this talk, we will mainly focus on these guys, the circular polarization states. And these guys, the circular polarization states, will interact with matter, because that's the aim of the talk, to make chiral matter to talk with chiral light. So for that, we will use, the title was mentioning, helically structured anisotropic material. One step backward, we define anisotropic materials in a very simple way. An anisotropic, let's go simple, uniaxial medium, represented for the physicist by a rod. This rod has typically three eigenvalues to describe its property, two of them being equal because it's uniaxial. And in the local frame, you have two dielectric permeabilities, parallel and perpendicular to the main axis of this rod that represents the physical characteristics of the material. If you want to go from this unique building block, this anisotropic structure, into a helically ordered anisotropic structure, you simply need to organize them in a helical fashion. So this is what this pictures is showing. Right-handed helix or left-handed helix. Remind the previous, the previous images of the previous slides. It's exactly the same. We have helical structured either electric field or material anisotropic optical axis. In that case, its theoretical description will be made by simply describing in the laboratory frame the dielectric tensors, the 9 components of the dielectric tensors. So describe the property of light propagating through or interacting with such a system, which implies that the displacement field will be connected with the electric field we were just talking about via this tensor. So to understand how it works, the interaction of helically structured light with helically structured material, actually we just need to resort to Maxwell's equation, and I would say, and then let the calculation occur, and you will have the answer. As I told you, let's grasp qualitatively what's going on, even for those who are not aware about the optics of chiral anisotropic material. And my guess is that we can understand quite easily what's going on. The point for that is to forget about Maxwell's equation at first, and just to remember, I will assume that we have a basic background in optics. The fact that when you are encountering a dielectric material, you will have an interaction with it like a window, and you will have some back reflection, the Fresnel reflection, for instance. And if you have a lot of this kind of layers, you will have a lot of micro reflections, a lot of backward spins. And depending on the way these backward elementary contributions are interfering one with another, and this comes with the periodicity of the dielectric properties, then you can have, let's say, in-phase micro reflections and resonant reflection. So this occurs in the general way for periodic dielectrics. In our case, we have a periodic system. It's an helical system. Every 2 pi rotation, you have reproduce the same pattern. So there is periodicity. We can expect resonant reflection. Second point, there is chirality. This is a fact. This is a starting point. If we have chirality plus resonant reflection, it means that we might have an answer from the material response, the light field, that will be chirality dependent, so polarization dependent, resonant reflection. So in that case, without knowing about Maxwell's equation in those media, it won't be a surprise if I state that this may happen. So have a selective reflection of one of the 2 circular polarization states interacting with the chiral anisotropic optical media. And this is a so-called circular Bragg reflection phenomenon. And this phenomenon, the selective reflection related to polarization states, is actually something you can, if you walk around in nature or in parks, maybe more in summertime than now, maybe the beetles are just hidden in the ground. You can, if you take the movie goggles, the circular polarization state polarizers, you can look at those animals, and depending on if you look at them using circular right or circular left polarizers, you will see different colors. Because their cuticle actually is endowed with this chiral anisotropic structures. So of course in lab we can do the same because we can engineer materials. And so this is just an example that illustrates another very important features of this circular Bragg reflection. Here it's just a reflectance spectrum. This is just the fact that there is a selective reflection and transmission. And here, this is the fact that for a given interaction, let's say this one, if you have the right wavelengths, you will be fully reflected. If you have another wavelength detuned from a given spectral range, which is called a bandgap, then you will have more transmission. So what is important is that that phenomenon is spectrally independent and corresponds to very generic physical manifestations, which is the bandgap. The fact that you have a spectral window where wave cannot propagate, which means if you resort to theoretical formalism, you won't have a no-load solution for those wave vectors. And we will use this kind of elements for the rest of the talk. And what is important is that this kind of structures, actually, the liquid crystals Rafik was presenting, are actually a very, I would say, usual way for optical physicists to deal with the circular Bragg reflection phenomenon very easily. Because actually liquid crystals, owing to their long-range orientational properties, can arrange in a various fashion. And one of the phase which is allowed is the nematic phase that Rafik was talking about, where every molecule is here parallel to the nearby. And then you have a local orientation given by a unit vector called the director, and referred here as the M vector. And this is anyway, anyhow, it's a fluid. So it's a birefringent fluid, which means that this soft material can be engineered in many ways, including in a helical fashion. But it's a bit more than that, because the long-range orientational order makes this helical arrangement spontaneous in some cases. You don't need to engineer molecule after molecule to put them into helical structures. So this is a so-called cholesteric phase. So for liquid crystal people, it's very well known. For others, the idea to have in mind is that you start with the nematic liquid crystals, and you add a little bit of chiral molecular dopants in a way that the molecular interaction will make every neighbor slightly twisted. It's a bit qualitative way to address it, but that's the spirit. And then, depending on the nature of the dopant, is it left-handed or right-handed, you will end with either a left-handed material helix or a right-handed material helix. And it is those structures that the cholesteric liquid crystals that are very well known for their colorful manifestations through the photonic band gap. And that I invite you to follow me with two examples that where the cholesteric liquid crystal optics can be used fruitfully in terms of physics point of view and also applied technology point of view beyond simply nice colors. And for that, I separate the talk into two parts. At first, I will discuss how we could use the circular photonic band gap to manipulate light, and how we can use, in the second step, how we can use the circular photonic band gap to manipulate matter. So we'll have the two sides, manipulating light or manipulating matter, owing to the circular photonic band gap. So let's start with how to manipulate light. So for that, and to understand what I mean by manipulation, I don't mean taking light and put it here at another place. It's like we have a light field, like this, the simplest light field, the paraxial light field, very simple expression, but everything is already here and ready for one discussion. Because what we missed in the discussion of the previous slides, where we were talking about polarization state, I missed to comment about this here. I was commenting about the propagation phase factor. But there is the amplitude factor. That may depend on space. This is trivial. My laser pointer is localized in space. Trivial. Which means it's bounded in a finite region of space. And there is variation of space. In space, the amplitude through space. How could we use the circular photonic band gap to shape the spatial properties of light? That is what we will address as a question. And for that, we need to, if we are in a framework of chirality, because as I told you that's the main word for this talk, we have to have a second look at the chiral properties of light. The first look we gave is associated with the helical structure of the electric field for circular polarization states, which is associated with a quantity, a mechanical quantity, which is called the spin angular momentum, and which is plus or minus h bar per photon for circularly polarized light. The second chiral information that emerges from paraxial light is embedded in the amplitude term. This amplitude actually can be also designed or conceived, just from a writing point of view, in a helical fashion. Simply, imagine you are simply writing mathematically that the amplitude factor is proportional to exponential EL5, by being the azimuthal angle in the transverse plane. This defines what we call an optical phase singularity, which means that the phase, here you have the phase map of such an expression for L equal 3, L equal minus 3, by the way, and in the central part, phi got all the values. If L equals 0, it could be any phi. So the phase is not defined, because it could be any phase in the same place. So we don't know what is the phase. And that's the vortex, that's the optical vortex, where we lost the information about the phase at that very place, which is the singularity as such.
And this is like a defect, yes?
It's a defect for the light field, exactly. It's ill-defined something. So even more than a defect, it's a singular defect. Because in liquid crystals, for instance, you could have non-singular defects as well, which means structures which are associated with a non-trivial topology, but not necessarily singular. So here it's really singular topological defects.
This is like cosmic strings.
Exactly. So here, the equiphase contains this information about the helical structures. Because if you plot the equiphase of such a simple complex number, you have this helical tree, you have this nice intertwined helices. Again, this is a chiral structure. This chiral structure is, similarly to the spin angular momentum, associated with another angular momentum content, this time of a phase of a special nature, and we call it orbital angular momentum. Orbit referring to spatial degrees of freedom. And we'll see that these two quantities are at the heart of this manipulation of light via circular photonic band gap, owing to a mediator. And the mediator is the phenomenon that will make these two quantities, polarization and spatial degrees of freedom, to talk one another. And this is the so-called spin-orbit interaction. And this comes by vocabulary because it's a coupling between the polarization space to the spatial degrees of freedom. And we'll try to explain how this spin-orbit interaction of light can allow the shaping light at will. So for that, I use a very simple anisotropic system. This is the optical axis. For those who are doing optics, let's say in a laboratory, maybe you already played with what is called half-wave retarder, which phase shift by pi orthogonal components of a light. And in that case, an incidence light circular polarization will come out of this half-wave plate with the opposite handedness. Right becomes left, red becomes blue. Sigma minus sigma. In that case, what is interesting is that if you look the phase of this field, you realize that the phase relationship between the two circular polarization, circularly polarized electric fields are related with the angle of the half-wave. Through this very simple relationship, which states that the difference of phase between the two, apart simply a propagating factor, is twice the sigma, plus or minus, right or left, times this angle. Which means that there is, in the phase, is embedded a spatial information that is read by light as it passes through the system. And this led, a long time ago, in 1997, Bandari to propose to use this geometric phase, which is really only related to a structural information, to shape optics, whatever optics. And here is a simple example he was proposing in this paper, a quadratic distribution of the optical axis of a space variant half-wave plate in order to have a quadratic phase information encoded in the optical beam. Quadratic phase profile is a lens, diverging or converging, but that's an optical element. In the context of spin-orbit interaction involving optical vortices, we just simply need to replace this quadratic profile with an azimuthal profile, for instance. And if you shape the optical axis in such a way, in a singular way, topological way, this topological charge of the number that you like to play with, in that case you will resort at the output with optical vortices formed via spin-orbit interaction. However, there is an important point here. This kind of elements, now you can buy high-tech companies or even medium-tech companies. You can buy geometric phase optics commercially. However, those geometric phase optical elements, they are based with the half-wave condition, which means that they are wavelength dependent by construction. So this is a strong chromatic operating condition which means for the user a monochromatic limitation. If I want to play with red, blue, and green, I need to buy 3 plates. Ideally, if you want to have a universal element, you want to be able to process all the elements in a single element. And this is what we can do with cholesteric liquid crystals. So the point to understand how chirality is coming, the idea is to start with something non-chiral, just to understand where chirality is game changing. If you play non-chiral, it means simply a structured half-wave plate. Optical axis with a given spatial distribution, and you have a given optical functionality at the object. There is a chromatic limitation, as I told you. This means that there is a bandwidth for the efficiency of the generation of your targeted phase profile, for instance, the vortex. We use vortex as an example here. The vortex generation, it's fully operating at a given wavelength lambda 0. It's narrowband, and that's it. You can't do anything. You have to deal with that. And then, as this technology was developed 15 years ago, some guys in the US proposed to introduce chirality and to twist this optical locally. So you have a structured half-wave plate, and on a given point in space, to structure in the thickness of the element to do something like that, to impart the structure some twist. So to start to twist, which means to start to embark chirality. And in that case, by doing this, so it's very complex technology because you need to have anisotropic, structured in 2D, and in the third dimension, you have also a structuration. It's quite terrific, technologically speaking. They were succeeding to do that, and to show that this is enhancing the chromatic performances. So very good. Everyone was happy, and some were able to bind into those elements and to do nice physics because they were like enhanced performance. But this is not that much ideal situation, it's just better. What we proposed, and this was done a work I did with Musha, we proposed to change a bit the situation, to change fully the situation, not just a bit. Not simply let's do better, no, let's do different. Let's do drastically different and drastically enough so that the system will become perfect. Is it possible? Yes, using photonic bandgap. Circular photonic bandgap. The idea was to say that, okay, if we can use cholesterics, which is spontaneously helically ordered, we get rid of high-tech technology. Nature is providing the twist. We just need to pattern in 2D, and technology is mature for that. It's fine. And then we were proposing this idea 5 years ago, exactly at the same moment as a Japanese group from Professor Masanori Ozaki. And we were demonstrating the physical, with Musha, the physical origin of this shaping, of this circular bandgap broadband geometric phase shaping, the geometrical nature. So that makes the difference in the sense that once you understand that, you can deploy what you know about geometric phase, and it was the case in our group, for the sake of this new technology, embarking cholesterics. And this is how it works, because let's just remind what I was presenting, the selective reflection, which is broadband, there is a spectra, there is a bandgap. And the point is that the idea is just to realize that the reflected light, the spin angular momentum of the reflected light, which is right and then circular polarized, reflected right and then circular polarized, is associated with spin angular momentum creeping plus h bar in the laboratory frame along the axis is reflected with minus h bar spin angular momentum. And this is exactly the inner recipe for geometric phase shaping through spin-orbit interaction. Then to realize this implies that helix structuring will lead to geometric phase shaping broadband by nature. So combining the geometric periphase physics with the Bragg physics of cholesterics, combining both in a single technology, Bragg-Berry technology. And this is what we did. So we started soon after the demonstration of the concept. it was published the same year, that's shaping the orientational position of the cholesteric helix in such a way, for instance, we were able to color is azimuthal orientation of the helix, it's same helix everywhere. Then we can generate broadband functionality here, broadband optical vortex generator, much more broadband than anything before. So it was, we were happy, we were excited, and we sit down, it's like, is this end of story and we move to the next project, or could we do even better? Because it's just a photonic bandgap is small like this, let's say 100 nanometer. Could we do all the visible spectrum at once, for instance? Maybe yes, is a trick. Let's parallelize this idea. One twist for one wavelength, a second twist for another wavelength, a third twist for a third wavelength, etc. Combining the bandgaps, piling up the bandgaps, piling up the effects. What does it mean? What is the translation of it? It's a gradient pitch cholesteric. If you are able to fabricate that, then you will have a super broadband geometric phase shape via BlackBerry photonics. How to do that? Nature, again, instead of high-tech approach, we go soft matter, we go liquid crystal physics. And we use not elastomeric liquid crystal as was mentioned in graphic, we are using glassy cholesterics, which means that below a given temperature, it's a glassy state, really like it, a glass. But there is an helix in that glass, an helix of the optical axis. So we pile up three blue helix, green helix, red helix, and you heat a bit the system. You just do that. If you heat, it will make both the glass transition, and there is interdiffusion, which means the discrete set of three pitches will be softened and will become a continuum between blue and green. Then you quench the system, you cool down the system at room temperature, and you have a solid state, gradient pitch, glassy cholesteric. And then you shape it in space, and then you have an ultra broadband BlackBerry vortex generator in that case. Still, so again, it was a good development, but remember that there is still a limitation which is not that small. There is a limitation that all this works for a given spin angular momentum state, for a given circular polarization state, because this photonic bandgap physics shaping is dependent on the polarization state. So all this is working only for a given polarization state. So you cannot use any light. This is a bit annoying. And this is very annoying in terms of spin orbit optics, because the beauty of spin orbit interaction is that space is addressed by polarization. And with this, you can do wonderful combination of structured light fields simply by playing with superposition of polarization state, which is very trivial. So you can achieve very complex structured light management simply with polarization preparation, something we are very used to do. So for that, those BlackBerry systems were very limited because they were only working from one of the two circular polarization states. The one which is reflected is processed, the other one is just going away. It's not useful. Here came a trick, is to realize that, this Moucher realized that actually, I guess he's an Indian guy in the US. I don't remember the name right now.
It was Laptakia. The mirror.
Yeah.
It was Laptakia.
So well-known guy in cholesteric physics, and he proposed an idea with another studies, simply to place a back mirror. If you place a back mirror to this system, what is happening? And you send whatever polarization state here, containing the two spin states. Let's say spin up will be BlackBerry shaped. Fine, we already talked about that. The other one passes through. There is a mirror. They go back. But once they go back by changing their helicity. So they flip their helicity. By doing so, now they feel the polystering. And they are very shaped here. So they go back again, they are back to the mirror. And the mirror is again flipping the helicity. Then they go back to the polystering. But now with a wrong helicity, and they pass through. And which means that you process both. One spin state, let's say spin down is processed from the front, and spin up processed from the back. It's very powerful because, for instance, if you have different shaping back and front, you can have very complex superpositions. And this is very useful for technologies where you are resorting to manipulation, superposition of states, as is done for quantum optics of structured light, for instance, where this kind of optical element might be useful. And this is experimental demonstration. Without the Hale mirror, you have a vortex for one spin state, and with the Hale mirror, you have broadband, whatever the polarization state. Now I'm moving to an extension in 3D. So another way to address the 3D. Just previously it was an helix structured in 2D plus a shaping in the third dimension, already 3D. But the helix axis is always in a given dimension. So it's basically, in terms of helical orientation in space, it is very poor. It's 1D. It's uniform. So recently we started with a colleague in France to use this kind of polysteric configuration where you have a hybrid boundary condition in parallel state and perpendicular states, which spontaneously, so again it's a natural process, it's not a technological process. There is a pattern formation driven areas where the polysteric is spontaneously organized. And this kind of structures is a biomimetic realization of what happens on the top of some beetles. Inspired by this, so we made this experiment. This is the one we fabricate. And we just study the properties. We look the polarization structure of it, from which we are collecting the information on the spatial distribution in 2D. We look by transmission telescope microscopy analysis and atomic force microscopy analysis. We resort how it goes in 3D, the distribution of everything. And we realize that the pitch is dependent not only on z-axis, but also on spatial coordinate. So it's and the optical axis of the helix is also 3D. So all this together, we're able to reconstruct the optical axis distribution, which is a full dependence on the phi angle, on the radial coordinate, on the longitudinal coordinate. It's fully 3D. And with this experimental knowledge, we can reconstruct the dielectric tensor. Owing is a model and embarking spatial rotations. I skip this. The point is that we can model the tensor in space at every point of the structure. Which means that we can learn from the structure by simulation. The structure is completely like non-3D. So what we can expect from it? It was, for us, it was not really, we are not expecting clearly clear things. So we analyze, we model, and this is what we model and that we observe. We observed a very interesting property, which is called here a spin orbit photonic diode. As you know, diode, you go through a diode system in one direction, it is blocking, and the other it is passing, 0, 1, backward, forward. Let's go the case for these structures. This structure, if you go from the photonic bandgap wavelengths, associated with the pitch of the polysteric structure here, the polysteric structure is here, you are reflected and nothing very interesting is happening. It's blocking state. You predict nothing, you observe nothing, but you are anyway. Then you do the same experiment opposite way. It's another pitch and it's 3D, and you have a wonderful interaction between the two spin states and the structure. Light can start to enter in, because it's detune from the bandgap, interact with the 3D environment of an isotropic medium, generate a contrast circular polarization states that is no longer interacting with the photonic bandgap, but anyway probing the spatial structure of the optical axis. Very complicated interaction. At the output, you have the transmittance of an optical vortex. Simulation experiment, it's worked very well. And this, for us, is so it's very, very fresh. We simulated a couple of weeks ago. We have new functionality for spin-orbit interaction that comes from a biomimetic sample. And we are stating that we might so far have missed many spin-orbit photonics properties of natural structures, including biological ones, which are very well known for the nice colors. And we would like to revisit all this colorful physics under the prism of spin-orbit Blackberry physics. So this makes me to move to the second part, which I will make shorter, which is manipulating matter. Just to give you another flavor, so we switch totally, no longer beam shaping here, but still interaction with the secular photonic bandgap of chiral material. So I will explain where the mechanical is coming, but you already have a flavor of it, because when I was introducing the secular polarization state, I was mentioning the spin angular momentum, a mechanical quantity, the ability to rotate an object. And I was also mentioning the orbital angular momentum, another capability to rotate matter. At the end of the day, all this is angular momentum. S and L as just sub-ingredients of the G, which you encounter everywhere. For those who are, for instance, playing with comments matter, atomic physics, you will see a big interaction of electrons. Here we deal with photons. And then I will introduce why and where chirality could be of interest there. Maybe it's not trivial at first, so let's have a look. The entry door for that is the last slide of the first part, biological systems. We are biological entities, and we are interacting with chiral systems, especially when we are ill, taking drugs to be cured. Because drugs are moleculars, organic compounds that interact with your body in a very specific and targeted way. You need to have, and biology is inherently chiral. So to properly interact with the biological entity, you need to interact most often with the right chirality. This is a well-known fact from pharmaceutics, that the drugs need to be prepared with the proper chirality in order to have the appropriate efficiency. If not, it could be even dramatic, like a poison or something that will cure you. There are many funny examples of this way, but you can have such kind of simple sketch summary. Either it works or it not works. That's it. And what you want to do is to be cured. So you want the right molecular entity, the right chiral entity. So for that, chemists, which are working there at the beginning of the chain to when you have to fabricate a drug, you start from building blocks, molecular reactants, and you make a chemical reaction to have the complex molecule that will do the job. These molecules need to be carved. So that's the ideal world. The real world and the real life of a chemist is usually that. You do the reactants, at the output you have your mass molecules, but you have also its mirror image. And this one is not good for the patient. So you need to separate them. Technology was developed, and this is working very well. Pharmaceutics works with this kind of tools, which are chromatography techniques, which are able to separate the right-handed from the left-handed entities of a given molecular configuration. And the pictorial image is this. You put the right and the left. They pass through a system, which is a phase. It's really a material system that will be selectively bind to one of the two chiral entities, capture it, and the other one is going through. So then either you collect what was bind or you collect it. And then you're done. It's very expensive technology. And as we know, medicine development is very expensive. It's also partly because of this kind of big tools, despite also the research and development. Very expensive tools. And there is another approach which is non-stationary, which is related with the mechanical effect. So not the passive interaction or at a given place, but really a dynamical action on the material to sort him. So it's mechanical sorting. I take the guy and put it at another place. So there is a very nice review from some colleagues on this topic. And all this has started a long time ago with Pasteur. Pasteur, who did the first dynamical mechanical separation. In the chiral language, we say chiral resolution. That's the way to separate the right from the left. And he did that at the macroscopic level with millimeter-sized crystals. At this time, it was tartric acid crystals, right and left. He needs to recognize the crystals, because the facets of the crystal, he recognized that they were either in one shape or another, when he was separating them, and afterwards to prove that he can separate the two chiralities and so on. So this needs two important things. An active recognition, it was the eye of Pasteur, and a mechanical action, it was really the real tweezer, it was really this object 200 years ago, to take the crystal and to put apart one from another. When I started the idea I will now just summarize, my motivation was to replace the eyes and the ends of Pasteur by things in general, conceptually. We will use something intangible instead of using like mechanical tools like your hands to do the job. I'm using a lot of light in my research, so could we use light to do the job? To send light, the light will do the job by itself. So we need kind of optical ends. And these optical ends should be sensitive to right or left, which means it should be zero. Circular polarization state could be of great help. And they could be of great help mechanically speaking, because a circular polarized light contains has some mechanical, I would say, strengths, its spin angular momentum. Some more than 1 century old, century, I'm exaggerating, 90 years old experiments showing that the spin angular momentum of light can exert a torque on matter was made by Beth in 1936 and by other mates around the same time. The idea in general is that you interact with the system, and when the system is modifying the angular momentum states of the light, mechanics tells you that a torque will be generated. So the fundamental principle, first principles of mechanics. Variation of the linear momentum forces, variation of the angular momentum torques. They're very, very fundamental things. Which means that circular polarized light will rotate matter. I will make the story short. But we want to place matter at one space or another. We want to separate. So we want forces, not torques. So here is the question, here was the challenge. How could I use circular polarization states? I reformulate. How could I use spin angular momentum to exert a force on the system? Which is a bit strange statement, because angular momentum is rotating matter. How could I use that to push matter? We need what we call in physics, very general language, crossed effect. I'm using a rotational quantity in order to have a translational response. So it's a cross effect. This cross effect means that I need, since at the end of the day I want a force, I need to change the linear momentum of light. But this should be spin dependent. Okay, this was the beginning of the talk. Because if we use helically structured anisotropic medium, we know that they are reflecting light in a discriminatory manner with respect to their spin up or spin down states, which means that you can activate optical forces with spin control. So this, 5 years before I was interested to that question experimentally, I just found this paper when I started, okay, let's do that because it was not done. I realized that there were only 2 theoretical papers, and then I decided to do the experiment. The challenge, anyway, is that if you want to target the chemistry, you have to deal with molecules. They are very small, the effects are very tiny, and the molecules are experiencing Brownian motion, very complex. To address the grain of this topic is very complex, because it's very tiny forces and you are annoyed by Brownian motion. So it's not yet achieved, it's just discussed theoretically so far. Then the way to address it anyway, experimentally, was simply to recall the polysteric structures, which are mirrors, and those mirrors are selectively reflecting light, which means they are selectively induced radiation pressure on the system. For this, we are developing a very simple material object, a sphere of helical structure, either solid or liquid. And we were showing that we can simply, by using 2 fields, 2 counterpropagating circular light fields, and sending a droplet in between those 2 fields. This is a collection of snapshots. And what you see from the top, this is a collection, this is a video summary, I would say. If it's non-chiral, it will be interacted the same way right and left, and it will go straight. And if it's chiral, left, it will more interact with one of the 2 states, right or left, and will be selectively deflected on the right or on the left. So it's passive, we don't need pre-recognition, light recognized and sort properly. So it's an optofluidic sorter. And the bandgap is just here to enhance the system, not to create the effect. The effect is really is there, whatever the amount of chirality. And then we extended it to tweezers as such, really the experiment of Pasteur. And we redid the experiment of Pasteur's, but without tweezers, with light, with vortex beams. So I will not go in details, but it is also another approach that we developed to use optical forces driven by spin in order to have sorting. And we generalized it not to a single entity for the proof of concept, but for a collection of objects, which is much more interesting. You have a mixture of left and right objects, like here, bright and dark. This is just by circular reflection recognition to identify, and this is the result. So we send beams, and the droplets are self-sorted in 2D and separated in a non-ambiguous way by doing so. So this is where we are in 2D sorting at the microscopic level so far. I would like you give me 2 more minutes. 1 minute. So I will exploit this 1 minute wisely, giving you a hint of interesting physics, fundamental physics we can do with a simple droplet of polysterics. We are able to reproduce analog Stern-Gerlach experiment, where the spin is the analog of chirality plus up, down, right, left, where the gradient of the magnetic field inducing a force is here, a gradient of optical helicity, and a force should be exerted on the system in a transverse manner. This was predicted a few years ago theoretically by 3 independent theoreticians group, and this was their picture. Stern-Gerlach experiment. You send a chiral molecules, it will be deflected up or down depending on its chiral state. So really analog of Stern-Gerlach is spin up, spin down. And then they were, even if they were optimistic, they were recognizing it was challenging. Reading that, I was like, whoa, we can do it with polysteric droplets. And this is what we built. We built a gradient of helicity, so I skip the details to fit the minute. And we place a droplet in the where the gradient is good, is optimal. And this is the picture. You see from top, so it's a constant intensity, but with helicity gradient, and the particle is placed here, the polysteric droplet, and is going right or left, simply depending on the relationship the gradient of velocity and the chirality of particle. And this leads me to the conclusion that K liquid crystals are more than nice colors, but it's nice physics. And I wish to continue this, not only with many collaborators and people around, but also with Armenian next generation, I hope.
Yes, thank you for your talk. Let's applaud the professor. The same hopes we also have here, that you will continue your job with next generation Armenian students. Are there any questions to Professor? Yes, please.
Probably this type of effects also will be present, for example, for electron beams, yes, if you structure some.
So electron beam, there is a mapping with light, although the electrons are spin-half particles, elementary particles, and photons are spin-1. Because so there is a spin-up, spin-down equivalent of secular right-left. And regarding the structure, regarding the spatial degrees of freedom, it has been formulated, it has been articulated in 2007, actually, that electron wave packets with properly structured phase, so really from the Dirac equation, from the basics, can exhibit vortex properties with orbital angular momentum mechanical content, very similar to what is in optics. And at the end of the day, it's this kind of mapping is going even beyond electrons. For neutrons as well, it is working. For any actually particles or objects. So because for any field you can describe this, as soon as you are in a scalar approximation of describing a field, which is let's say the first approximation. If you have a scalar field, you can have, as I was showing here, the paraxial field is a scalar description. And if I remove polarization state, I have the scalar field. The scalar field can be endowed with a spatial structure, orbital angular momentum. So if I got a scalar field with the spin properties, I will turn it into like this. If I combine it, so as I have this light, then I have spin-orbit interaction and all this kind of shaping and physics. So for instance, for electrons, so any particles can be described as field. So we go to quantum mechanics and then we are happy. But if you are dealing with a field associated with a spin, then you are done. You have spin-orbit interaction, and then you can do all this. For instance, several groups are working towards spin-orbit interaction of electrons and to build machines to shape electrons in the same way that we are shaping light, playing with structured magnetic field. So it's really not that trivial, but it's really an idea that is pushed in the community. So yes, it's really like all this goes beyond light.
Okay, thank you. Other questions? Yes, please.
Yeah, about creating the left-handed and right-handed helix, you said you're adding dopant. How it works? Well, why it becomes right to left?
Okay, so you could have like a macroscopic mechanical picture. This is the road. If you pile up roads, they will pile up one over another. There is no reason for the spontaneous twist. No, imagine I have in between two roads, I got my end. My end is chiral. It has the flavor of an helix. Then I place another road above. This road will feel the flavor of an helix here. So it will interact with this chirality. Will be a bit twisted. And again, and again, and again. And then the point is that when you have a chiral molecule interacting with a non-chiral molecule, the interaction there is some spatial symmetry breaking in the interaction, the electronic forces at the molecular scale, that makes the molecules to be slightly tilted one to another. And then you continue this at the scale of the macroscopic scale, and then you have a spontaneous emergence of an helix. It comes from a spatially broken symmetry of intermolecular interaction.
About the ion separation, like what properties of the particles are important? You name them particles, molecules.
What is important is chirality only.
Only.
Like,
The
yes.
speed, like the mass, I don't know what, you know, this
It
kind
could be a glucose molecule. Take sugar at your next lunch. Take sugar, it's chiral. Glucose molecule, you could, they are chiral. They interact in a selective way with chiral light. But this interaction is very weak at the molecular scale. But still, the physics is there. So technically it works, and that is why these days, since 5 years, since the first experiment emerged, now there is a lot of theoretical works at the molecular scale, showing many strategies to do the job, but no any experimental realization, because it's today it's still not yet doable, I would say, or the smart ideas are not yet popped up to realize this. But we are also working in that direction to go towards small spatial scales. So it's a long journey, but I would say a researcher will do it one day or another.
Okay, thank you for your answer.
Thank you.
Other questions? There are none. Okay, so now we will have a group picture, group photo, and after that till 4:15 we will have coffee break. After which till 4:40 we will have our chapter presentations, chapter poster presentations. And please feel free to have coffee break and come here to have a group